have at least like, you want like 2 levels of cache. Okay, so if you're about to speed your processor, I got a 3 gigahertz processor.
I know this is very procedural the way I'm doing it.
Let's see. Should I try to make this somewhat realistic? Or should I try to make it difficult? Difficult.
Yeah.
Then I won't allow writes. Pass writes.
No.
Do you want me to do instruction and data separate? Or just to do data? Okay, so I got a gigahertz processor, let's say.
You gotta go and
Let's give him a camera.
So I need a load amount, I need a store amount. Let's see, loads, usually loads are somewhere, say 20 to 30%. 25 good?
Okay.
But then wasn't that what he was trying to say?
Stores are normally 5%, give or take a little bit. As it's going on, 5%, 10%, something like that. You care, Rich?
5%.
5%?
So that's equal to 30, yeah. I already wrote that.
Okay. Let's assume everything else is ideal,
Okay.
just for simplicity's sake. Although, I mean, we could add in a branch predictor if we wanted.
You're going to be that.
The only disadvantage to that one is that, we can't have cascade possibilities.
Yeah.
So let's see, then we need a level 1 cache. Let's see. So it needs an access time. Let's say our access time is 300 picoseconds. Sound fair?
Yeah.
So we have instruction and data. For our instruction, do you want me to go through all the kind of justification stuff or just the numbers?
No, just the numbers.
Just the numbers.
Yeah.
Okay, so let's say my instruction, the miss rate is, let's say, 1%. And on my data, let's say my miss rate is 2%. Normally, it'd actually probably be like 1 and some change.
Okay. Yeah.
But it just, this will just be faster to calculate. If, just as an advance notice, if you see funny numbers that are in any of my test problems, you should immediately think it was customized to make it really easy to calculate. Okay? So you will something, like if I stick a fraction in there, like it says 1/6 or 1/9 or something like that, you can pretty darn well better believe that 1/9 ought to cancel something. That's the only, I mean, in real life, such things won't happen. But in tests, you don't have all your calculation devices because I don't let you take a calculator. If you can't calculate it, set up the problem completely correctly. Don't calculate a darn thing and say, at this point I would enter it into my calculator. If you set it up correctly, I will give you full credit. Okay? Because I presume at that point you would. I don't allow calculators and other stuff because people cheat. It's a sad reality, but they do. So, since all of you are honest, you don't want that one evil person coming in and scoring something high. There is no curve, but it makes you feel bad anyway. So, I just remove that possibility. There's no electronic devices up there, so if I see one, you failed, right? So that's the end of that problem. So, in this case, I either give you easy numbers, right? If the numbers are really set up to be easy, you should try. Just look at them and try. If you run into a serious problem, then you can give that little, quote statement, but you ought to be able to ballpark it, because sometimes I'll ask you to compare. So you ought to be able to look at it and be able to at least ballpark the thing and be able to say, this is bigger than that. If you get to that level, even if you don't calculate it, I'm perfectly cool. Does that make sense as you're going? But if you see things, you see, I can give you, 12 21st or something dumb like that. It's going to cancel something. If it does not, you did something wrong. And that is my promise. It's checkable. That way you can sanity it. On these type of things where I'm throwing them on the board, I have no idea if it'll work out. So I work them through and then I tweak the numbers for the ones on the actual test. All right, so I've got my access time, I've got my miss rates as it's going. At this point, I'm going to assume it's a right through. Right through cache. And you know, we have to have some idea about the block sizes that it's going to go, because I have to know how much stuff is going to load on. Now, for this one, it's going to have a smaller block than the level below it.
Yeah.
Okay? Which means, in essence, unless I specify a network between here, that you have to transmit it, which will determine how many accesses go on. So that would be my next question. Do you want me to put a network in here?
No.
Or do we, okay, so we just assume that it can then fill the block in
Yeah.
one transfer. Okay. Not too bad if it's a level 1 and level 2 both on chip. So level 2 cache, so I won't have to worry about the network there. Access time to that. Access time is usually a reflection of how much work has to be done or how far away it is. So once I get to a bigger cache, I probably have to do a little more work. I want to put all kinds of victim buffers. I want to check more places. It'll probably cost me a little bit more. So I'm going to jump from like about 300 picoseconds, which I was trying to make it fairly fast. I'll jump down to something that's probably going to be, you know, I don't know, let's say like 4 nanoseconds or something. Okay? It's going to be slower, but it's protected by the other stuff above, so what do I care? I can pay a little bit of a penalty. I'm only doing it a fraction of the time. So its net effect is going to be very small.
Okay.
So at this point, usually you're unified at the level 2 zone. So I can just say, you know, my miss rate at this point, and your miss rate is typically at this stage, say, somewhere between like 15 to 30%. Typically, fairly typical numbers for miss rates in here. Again, part of that reason is since this is a write through, whatever size this cache is copied right out of here. They're duplicated. That way this one can dump its stuff real quick and doesn't have to worry about it. So this one I can only use a portion of it. But also it's that problem of it's further away, and the further away you are, the less likely something gets hit anyway. So we'll say in this case, miss rate 25%.
Yeah.
There.
Okay.
In this case, I do kind of have to mention a block because I probably will have a network that's going down to my RAM that's going on.
Oh, it's 64 kilobytes?
So 64K is a little bit big to load into cache,
Yeah.
right? Because a K is 1,000 that's going on, which means about 250 variables per K.
Okay.
So you're probably not pulling 250 variables at a time across there. But I might have something like, say, like 128 bytes.
Okay.
You know, would not be an unreasonable size as it goes on. So let's just pick that as our number, right? 128. That's the byte block. That's big, but it's, you know, it's doable. And I could have a 64-byte block. Into that sort of. If I'm talking here with a 128-byte block, how many variables?
6.
It is related to 5,
2.
which is
32, 4, 8, 32, 64, 128. So then that would be
2 to the
divided
7th is 128.
32.
Okay.
All right. So if I got 128 bytes, how big is an average variable?
5, 7 bits.
You know, a variable?
What do you mean
That's
variable?
no, it's right. I've got a 128 byte block.
Okay.
Right? That's how big a block is I'm loading from RAM.
Okay.
If I'm loading a 128 byte block, how many variables can I stick in that block? Is that a reasonable question? Okay. So now we got to ask the question: how big is a variable?
Yeah.
4 bytes? Or did it?
4 bytes is if I'm dealing with like a basic int on a 32-bit machine. So 4 would be one reasonable thing. Any other reasonable numbers? Right. So 4 bytes is either a 32-bit int, right, or a single precision floating point number, a float. Those are reasonable numbers, right?
Yeah.
Any other reasonable numbers I could assume? Could I have 8 bytes? Right? That's a 64-bit int. There's a lot of 64-bit, computer systems out there. So that's how big your int is that you're loading. Right? Or a double. So if you declare doubles in terms of floating point numbers, a double is going to take you 8 bytes. This is most likely where you're going to pay is one of these two. So if I have 4-byte variables, how many variables can I fit in 128 bytes?
4.
What?
By 4.
Okay, which is?
32.
32. Right? Don't make this harder than it is. Right? 2 to the 7th is going to be the size for 128. If you're going to divide by 4, which is 2 to the 2. I know everybody goes, oh my God, exponents, that's ugly. But it's not, because I would never actually write this out. To divide exponents, I just subtract the numbers. This is equal 2 to the 7th minus 2, which is 2 to the 5th. 2 to the 5th is one of those numbers, as a computer person, you should just memorize. Right? Now, there's not a lot of things I say you should just memorize. This is one of them. Okay? 2 to the 5th is 32. So you just get, hey, that's 32. So I can get 32. If I go to 8 bytes, what's going to happen?
You have to go to 6.
How many of them? If it's twice as big of a things, I can fit half as much in there, so it's 16. Or you could just go, oh, it's 8, so I'm dividing by 2 to the 3rd. So you get 7 minus 3, which is 4, 2 to the 4th is 16. Whichever way you want to think about it. So, in other words, I'm loading either 16 or 32 things at a time. It's a fairly decent sized load. When you look at things, you don't necessarily want to spend tons of time, but you want to get to the point where you look and you say, I know what that means. I can see an implication of this. I left a gap. Why do you think I left a gap?
Because there's something.
There's something I should tell you there, right? Right. This is a right-through cache. What do you think this one's going to be?
Right back.
A right back. Why would I make a right back here and a right through there?
Because
After RAM is really.
Access to RAM and across that bus costs a lot. So therefore I don't want to do it very much, so I want to write that, which will kind of aggregate together a bunch of writes before it sends it out. Because remember, I've got 16 to 32 things. If you're accessing this in a vector sense, I don't want to update RAM 32 times. I'd rather update cache 32 times than do one RAM update. It's a lot cheaper that way. So I want to aggregate the writes together, combine them. Does that make sense? Okay, so this one is going to be a write-back cache, which means it has another percentage I have to tell you. Dirty. What does dirty mean?
Tells the validity of the cache content.
It means that I have updated the cache. I haven't updated RAM for that spot yet. So if you eject it, you're going to have to update RAM. So you'll have to pay for another RAM access on top of whatever else you're doing. So it tells you the likelihood that you end up having to do an extra RAM update. That make sense? Usually that's fairly low, say anywhere from 10 to 25% or so. So for simplicity, I'm just going to pay 10%. Gives me a nice number. So far, so good? Okay. At this point, I now have to talk about RAM. Right? So now my RAM, I have to have an access time, I have to have a number of bytes I can transmit simultaneously, and usually I have a burst writability that goes on. Okay, so for my RAM, initial access, let me say it's 50 nanoseconds. Let's pick a nice clean number. All right, let's say I've got a DDR system that's, running at, let's say, 500 megahertz. Okay? What does DDR mean?
Double data.
Double data rate, right? That means I can transmit on the high and the low pulse. So on that clock, when it goes high and when it goes low, I can send a different transmission each time. So essentially, I can transmit twice as much as I normally do. If I tell you I've got 500 megahertz clock and double data rate, what's my effective transmission frequency?
1 over 2 times 500.
So I'd be translating at 2 times 500, which is a gigahertz. So the time between it would be
1 over.
1 over a gigahertz, which is a nanosecond.
Okay.
Right? A gigahertz is 1 over a nanosecond. Another one of those things just to get used to. A gigahertz is 10 to the 9th. A nanosecond is 10 to the minus 9th. So getting those prefixes down. There's not a lot of them. You just really have to remember the ones, for, kilo, mega, giga, as it goes up. So you only remember the 1,000 blocks. There's not too many of them. There's like 5 we used. Okay, so that means 50 nanoseconds, and therefore I can write at 1 every nanosecond, given that clock. So that means my bursts are going to be at a 1 nanosecond burst. Fair? Now, I'll be nice in this particular case, just for the sake of time on here. I could give it to you in bits. I could give it to you in bytes, how much the data package is that it sends at the time. Let's say in this particular case, I'm going to send 16 bytes at a time across my chain. Fair? So each transmission is 16 bytes per transmit. Good? At this point, can I calculate stuff?
Yeah, you have an access time, 100%.
All right. Which is the easiest way to work out costs for access times? Bottom up. Much easier, bottom up. So I suggest you do it that way. Right? Usually I try to ask it this way on tests. You will watch on the test, I'll ask you, how much does it cost you to access RAM? I'm deliberately trying to lead you through the easy way of calculating. If you listen to what I am doing, it will make your life simple. The danger is it does cascade. So make sure you're clear on each step. This is my basic rule. If you make a mistake on a step, at the next step, if that costs you, I will recalculate. So please don't do this too much. Okay? But I will actually recalculate to see whether or not, that made the difference. If it was only the earlier problem's number mistake that affects it, the rest is correct, you will get full credit for the later stuff. You only pay for the penalty you make, not for everything that cascades. Right, so I let you know that so you are calm. Calm people do better, right? Which means it's easier for me to grade. So don't mess up. I don't want to do work.
Don't mess up or you all fail.
Okay, so first one, how do I calculate the access time for RAM? The effective access time for a memory access to RAM. And it ain't
50 now.
It's not 50. Because when I do an access, an overall, right, the first access that's in here just says to just get the addresses in there, get the first block of 16. But when I'm really doing an effective access, I'm not just getting 16 bytes, am I? How much am I getting?
128.
I'm getting 128 bytes. So the first one cost me 50, 1 nanosecond for each other one. How many total do I need?
And 128 divided by 16 is going to be 8.
8. This is not that hard, right? Do it the fast way. 2 to the 7th, that's 128. 16 is 4, so I just 128 divided by 16. That's 2 to the 3rd, that's 8. Done. You can do that in your head. Okay? The reason why we like powers of 2 is A, they appear all over the place, and B, they make it really simple for us to calculate if we know the rules. Okay? So take advantage of them. This is why we love logarithms. Logarithms and exponents are extremely efficient for calculation. So I need to do 8 accesses. First one costs 50, the rest of them cost 7, so it's 50 plus 7 times 1 in nanoseconds.
Would it be 8? Why 7? Sorry.
How many accesses are you doing?
I thought it was going to take 8.
8. First one,
Oh.
remaining 7.
Okay.
Make sense? Okay, so I now know how much any time level 2 cache has to talk to RAM. That's what RAM has to do because I have to handle the entire block. I can't just do part of it. So now I know effectively what that level does. I am done with it. I move on. I've already used this piece of information. I don't need it again. So now I just have to deal with the remaining numbers. What's the effective access time to level 2?
4.
It's going to be that plus.
Like 10%.
Base cost plus probability times penalty.
So it's going to be
Right.
this rate times.
What's the base cost? 4. What's the probability? Probability of a penalty is 0.25, your miss rate. It's the probability of a penalty. What's the penalty I have to pay?
57 nanoseconds.
I have to go down to RAM. It's going to cost me 57 nanoseconds. Am I done?
No, you're 30 bit now.
30 bit.
All right. There is, so I'll write this out the painful way and then I'll combine it because everybody looked at me strange when I combined them together before. All right. There's also a 10% chance that I have to, when my new data that just came in, I've got to be able to clear out space for it, and that space could be dirty. So I might have to write that stuff back down. So 10% of the time I've got to write the stuff back down.
And that's going to take
Right.
57 nanoseconds.
So that 10% of the time, when I had a miss rate, when I missed, it only happens when I miss. If I didn't miss, I wouldn't pay that because I hit. I've got space for it. So, 10% of the time when I missed, I have to pay the access time again because I had to write. Does that make sense? Now we notice this looks a hell of a lot like this. As a matter of fact, we can even just say that this is this times 1. Distributive property says 1 times the thing plus 0.1 times the same thing is 1.1 times that thing. Yes?
Yeah.
So this is why when I normally do this, I don't write all this out because I am lazy and this wastes my time. I just go, I say, I automatically have to pay the access to RAM for the thing I access, and 10% of the time, I have to clean up the dirt. So I just go 1 point dirty. And it takes care of that automatically. It's distributed already through. Make sense?
Yep. That's going to give you.
I can calculate this out. I don't need the 1 anymore there. All right, so a quarter of 56 is 19. So I got 19.25 times 1.1 which is going to give me, what, 21.175? Plus that gives me 25.175. Tell me if I'm right.
0.25 times 7 times 1, 15.6 plus 4, 19.6.
Okay.
Because I got 4.25 times
Because
7.
this should be
15.
19.25, right?
Let me check that. 0.25 times 7, 14.25.
Oh, you're right, because that's 15, yes, so that's my, so I'm off by 5. So you sure about the error, because it's 14.25, and then I'd have to add, okay, so.
No, after that multiplication, you get 15.6.
Yeah, so 15.675.
And then you add 4.
19.675.
Yeah, there we go.
All right. So we get 19.675. That's this. We now know what this is. This aggregates everything below it.
Yeah.
So I never have to touch anything again. I only have to deal with that number. Huh? I go to the next level up. The next level up, how do I calculate that?
It's going to be effective access time plus the missed rate.
300 picoseconds, which is 0.3 nanoseconds.
Yeah.
Right? Pico's one level down from nano. 300 turns into 0.3 nanoseconds.
Yeah.
So I've got 0.3 nanoseconds from this. And what do I have to pay?
1% of the time you pay 19.6, and then 2% of the time you pay the 19.6. So it would be.
So this is actually one of those fun things. You have to separate the access times now because there's two different sides.
Okay.
Right? So we have to say there's an instruction value and a data value. Both of them pay the 0.3 nanoseconds. For the instructions, I pay 0.01. For the data, I pay 0.02.
Yeah.
And this is the 19.675, and this is the 19.675. Agree?
Yes.
All right, so let's see, that's about 1/50th. So this one was easy. All right, so I get shifted to 1, so I get 0.49675. So I should be up to 0.6.
Damn, you're good.
Well, it's just, I mean, it's not as fancy as it looks.
Yeah.
All I have to do is just shift 2 decimal places. I did 3
And then
plus
add.
1 is 4.
Okay.
And then I copy the rest of the digits. So if I screw that one up, I'm in deep trouble. Right. And then I'm adding almost 0.2.
Okay.
Right? So it's 0.2, and then I just have to take off 325. So I just add 0.2, which gets me to the 6, 9, 375, and I take off the 325, which gets me 3.5. That should be that one.
Nice.
Now, realize you can calculate fairly easy if you check through. Most of these are designed to be able to do. I expect you can do these. There are strange screwbally spots that you might run into, errors as it goes, but it's a good habit to get in. Several reasons, right? There are times you don't happen to have your electronic device on you to do your calculator, somebody asks you to ballpark something. Okay? It's always at the darn most inconvenient time somebody asks you to do something. So you ought to have an idea. Number 2, sometimes your electronic device calculates incorrectly. You hit a wrong key, you know, it itself has a glitch inside of it. I don't care what the situation is. If you can't ballpark what that's going to be, like even in these cases, you could have easily went, you know, this is essentially 20. 20 times 0.02 is going to give you 0.4, so it should be a little bit less than 0.7.
Yeah.
And you would have been pretty darn close. Very, very fast. That's what I was saying. Even if you don't calculate it exactly, You got to be able to ballpark it quickly. The ballpark is actually often more important than anything else, because that's the way you sanity check your numbers. Final advocation to you is, I imagine most of you probably do not want to suffer from Alzheimer's and the rest of that stuff when you get old. It's shown that people who do a lot of mathematics and other stuff throughout their life tend to keep their brains more flexible, and they are less prone to develop symptoms of Alzheimer's and other memory problems. So I encourage you not to completely rely upon the device also for that one, because you don't want to be the person who forgot your name at age 70. Right? Kind of sucks. Okay, we good? Now we go up to the next stage. Now we just have to combine together. Now I know this is everything in cash, depending on whichever side you're at, for instruction or data.
Yep.
So I just have to pick what I need off of them. These are now in nanoseconds. I have to turn them into cycles. How do I turn them into cycles?
1 over 3 gigahertz.
So I just, actually you take 3 gigahertz, multiply by nanoseconds. Because a gigahertz is a cycle per nanosecond. That's what the unit is. Cycles per nanoseconds times nanoseconds is cycles. So if you just multiply by 3 gigahertz for the next level up, like the nanoseconds and the gigahertz will cancel out and give you cycles. So I get 3 times this, which will be just a little bit less than 1.5. Right? And 3 times this will be a little bit less than 2.1. Fair enough? So now I'm just kind of rounding at this point, but it's good enough for sake of argument. Okay, so now I've got cycles. So now I can come in and say, how often do each one of these apply? Well, my CPI for my system is going to be ideal 1. Plus, how often do I encounter an instruction penalty?
0.25% of the time you do a load.
I do a load of what?
Load of data.
Data. So how often do I get the instruction penalty?
5% of the time. Or no.
5% for a store, which is a store of data. So both of these numbers relate to data. How often do you have to fetch an instruction?
Only when you're calculating, so one.
Only when I'm fetching an instruction, right?
Yeah.
So how often do you fetch an instruction? How many instructions need to be fetched, and how many do you just know automatically?
You fetch all of them.
Ah, so how often you got to pay that instruction penalty?
Every time.
Every single time. So you just pay that. Chance you hit an instruction, 100%. Right? Cost of instruction, 1.5. See why I don't like to pay this? So even this is actually quite painful. And so at this point, this thing I would want to get rid of. And this is a common question after I have you answer this, is I usually ask something like, if you were going to improve something, where would you put your effort?
Improving your instruction.
That one's going to cost me 1.5 for my CPI. And the likelihood anything else is going to cost me 1.5 is pretty low, because the rest of them, I've already got a fraction reducing them down.
Yeah.
So that one's going to kill me, even though it's small. Okay. How often do I encounter a load penalty?
25%.
25%. What's the load penalty?
25.
Your data.
So 0.25.
How often do I encounter a store penalty?
0.05.
0.05. What's its penalty?
2.1.
Same thing. Because I said in this case, you told me give you a bad machine, a machine that had problems. I said I can't continue past writes. So I make it send the write all the way down to the bottom, and then when it says okay, it's been handled, then I can move on to my next instruction. Is that realistic?
No.
No, it's not realistic. You know, everybody continues past them because it doesn't matter. You trust that your cache is going to take care of it for you, so you just keep on going. It would be kind of silly to hire a personal assistant and then walk around behind your personal assistant and see if they did what you said. Right? Cache is the personal assistant for the CPU. It makes no sense for the CPU to then check every single thing that goes on. Right? Just don't have it at that point. So in our case, they're both the same, so I would just add them together, which would give me 0.3 times 2.1. Which is going to give me 0.63 as it goes on. So, it's somewhere around 40% of the cost of those instruction loads.
If we were to continue past rights, it would be 0.25 times 2.
It would be 0.25 if you continue past. And that's
Because they
cheap to
ignore the
do,
source.
so there's no reason why you wouldn't.
I see a test question.
Well, these are the types of things I could ask you. It shows, do you understand? Because there's two types of things. There's, do you get the numbers, and do you understand what the heck those numbers mean? I have to check both. We good?
Yes.
So, we now have CPI. What could I do with that CPI? Could I ask you, what if I asked you, what's the performance increase of this over a system with no cache? Would that be fair?
What's
The performance increase of this system over a system that does not have cache. Same computer, no cache. This computer with cache. What's the performance difference? Because that might be reasonable to just find out how much. I mean, we see the numbers, we go, okay, yeah, there's a number, right? How much does it mean if I didn't have cache? Reasonable? So we've got an answer here, right? So that's 0.63, 2.5, so we're what, 3.1 or something is my CPI. Just get a ballpark. So what would this cost if there was no cache?
So we're going for RAM.
So I would go straight to RAM every single time.
Ouch.
Okay, now I wouldn't have to do this access, would I? Because I could just load my individual particular answer, and this thing can send up to 16 bytes at a time. That's more than any variable I need. I only have to pay the 50, don't I? For everything, yes. Okay. So now that's 50 nanoseconds. How many cycles is that? 50 times 3 gigahertz means 150 cycles. All right? Well, we want to see what are we looking at here. So my CPI, I can jump right to CPI because there's no intermediate layers. It's 1 plus the cost to load an instruction, that's 150 cycles. Then it might be a store. Or it could be a write. There's no way you can continue past writes, and this time you have to write to the RAM. So I just can lump them together, 0.3 times the cost it takes to access them. On the bright side, you don't have to pay for the dirty. It's right there, okay? No delays, right to RAM. That's awesome, right? So 0.3 times 150. So that's 45, 195, 196. Look at that blazing access, right? 0.3 is the data accesses. 25% loads, 5% stores. Together, that's usually 0.3 data accesses. Awesome, eh?
That's what I want.
This is a blinding CPI. So, number of instructions, has it changed? Clock, has it changed?
No.
So all I have to do is look at the ratio of the CPIs to see my performance. So the speed up of the system with cache is the old 196 divided by the new 3.1. It's the speed up of putting cache on. This is roughly 3, right? So we're like 65 or something like that. Fairly worthwhile. Put maybe a few megs in cache. Yeah, 65 times speed up on your system. Probably worthwhile. Right? So it's kind of one of those fun things to actually look at, see where it goes.
Cool.
Good?
Thank you.
All right.
I'll have another quick one for you on Wednesday.
Trey, awesome.
Sorry we kept you late, though.
Oh, no, it's about right.
Okay. Wait, picture time.
Have a lovely day, all.
You too.
Slowing me down.
No, take it out.
So it's the hard drive, right?
No, I don't have a hard drive. I have an SSD.
So it's that speed. You need to hook up your SSD to the RAM slot.
No, I want SSD on chip.
Need this.
We'll go down.
Taylor, build it.
You want one?
Do it, Taylor.
So it's like a CPU with 1 terabyte of cache.
Yeah.
L weekend. Do you want your L?
Go get out.
Dog. The dog is like,
Oh, by the way, Cal mentioned a little bit what she's going to talk about on the test. And I was like, I don't remember.
311.
that doesn't really work. Talking about, I can't even hold it. Star and then like some stable. I leave it like reminds me of my girlfriend. Watching the test, she starts laughing. And Chow calls me out for disturbing class. And she's like, "What did you? Taylor has something to share with the class." I'm like, "Oh." So I totally set it out in the middle of class. Everyone started cracking up. I totally just turned it on her so bad. It's funny.
She made it even worse.
Yeah, she made it even worse. Totally in the class even more.
How far did you get in lab 4? Did you finish the fetch part? I know you were
I
working
think so.
on
I
it.
didn't test it.
I think it's 311.
Can you send it to me? I'll take a look at it. Okay, cool.
You have 1 minute.
I put in the, I put the whole.